for which positive real number x is x to the power 1 over x, the largest, for which integer n is n to the 1 over n, the largest, which is larger, 3 to the power 1 over 3 or pi to the power 1 over pi. To determine x so that x to the 1 over x is the largest, we will need to optimize x to the power 1 over x. So this will be our objective function. To find the derivative of x to the 1 over x, we rewrite this as e to the ln of x to the power 1 over x. Note that e ln canceled out, so we will end up with x to the power 1 over x, but we introduce this so that we can write this as 1 over x times ln of x. Using the exponential and the chain rule, f prime of x is e to the 1 over x times ln of x. With the chain rule, we multiply the derivative of the inner function, which is the exponent, using the product rule. The derivative of 1 over x is negative 1 over x squared. We keep the second factor plus 1 over x times the derivative of ln of x is 1 over x. This is e to the power 1 over x ln of x times negative ln of x over x squared plus 1 over x squared. We introduce e ln so that we can use the product rule to differentiate f of x. Now that we're done, we no longer need it, so we rewrite this first derivative f prime of x as e ln of x to the 1 over x. Inside the bracket, we can combine them because they have the same denominator. 1 minus ln of x over x squared. This is x to the power 1 over x times 1 minus ln of x over x squared. We then set this equal to 0 to determine critical points. Now, we are only interested in positive x, so even the derivative is undefined at x equals 0, we don't need to check it. We only need to check x greater than 0, positive numbers only. This derivative is 0 when 1 minus ln of x equals 0, or ln of x equals 1 when x equals e. ln of e is 1. There is only one critical number here. We then check the sign chart of f prime on the interval 0 to infinity with the cut point e. We see that for any number between 0 to e, such as 1, ln of 1 is 0, 1 minus 0 is positive, and so f prime is positive for x between 0 and e. For any number between e and infinity, 1000 for example, ln of 1000 and then 1 minus ln of 1000 is negative, so f prime is negative. We see that the quantity is increasing and then decreasing. This means that we will have a maximum at x equals e, and there is only one critical number on the open interval. This is also the absolute maximum. We conclude that the possible x where x to the power 1 over x is largest is when x equals e. The function x to the power 1 over x is increasing from 0 to e and decreasing from e to infinity. The integers where e is between are 2 and 3. Although we know that 2 is in the increasing interval and 3 is in the decreasing interval, we can't tell immediately which one is higher, 2 to the 1 over 2 or 3 to the 1 over 3 power, because both of them are more than 1. Instead, we will compare the sixth power of these two, because 1/2 and 1/3 has the least common denominator of 6. 2 to the 1/2 raised to the sixth power is 2 cubed or 8. 3 to the 1/3 raised to the sixth power is 3 squared, which is 9. Since 8 is less than 9 and the sixth power is 1-to-1 for positive input, we see that 2 to the 1/2 is less than 3 to the 1/3. Although 2 is still in the increasing interval and 3 is in the decreasing interval, 3 to the 1/3 is more than 2 to the 1/2. It might have something to do with E being a number that is closer to 3. E is roughly 2.7. Next, which is larger, 3 to the 1/3 or pi to the 1 over pi? It is simple in this case because both 3 and pi are in the decreasing interval. The function f of x equals x to the 1 over x is decreasing on the interval e to infinity, and both 3 and pi are in this interval. If the function is decreasing and if x1 is less than x2, then f of x1 has to be greater than f of x2. We see that 3 is less than pi. This function is decreasing on the interval e to infinity, so f of 3 has to be greater than f of pi. But f of 3 is 3 to the 1/3, and f of pi is pi to the 1 over pi. So between the two numbers, 3 to the power 1 over 3 is larger.